Today's objectives, you'll be able to define electron configuration, so you'll be able to tell me what it is, what's an electron configuration. You'll be able to describe and give names for the three principles that guide how electrons fill their orbitals. And then you'll be able to actually use all three forms of notation for electron configurations. You're going to learn how to do orbital notation, how to do electron configuration notation, and how to do noble gas notation. So be looking out for those things. If you can't do all of those things by the end of class, then come chat with me and we'll figure it out. So the quantum model that we just covered is superior to the other models that we've discussed because it actually allows us to describe the electron configuration for atoms that are not hydrogen. Okay, electron configuration is going to be the arrangement of electrons in an atom. So when I'm talking to you about electron configuration, what I'm saying is a way to describe how electrons are arranged in an atom. Okay? Like everything in nature, atoms are seeking to have the lowest possible energy state. Okay? They don't want a high energy state because it's not as stable for them. They want a low energy state. We've already sort of talked about this because when we talked about the Bohr model, we talked about electrons having a ground state. All that a ground state is the lowest possible energy arrangement of electrons. So what shape around the atom, what configuration of electrons is the lowest level of energy possible for that atom? That is that atom's ground state. While real atoms that exist out in nature are not built one proton and one electron at a time, today you're going to hear me talk a lot about, and if we add one more electron, or if another electron joins this atom. That's not how things happen in nature, but it's really convenient for talking about how we build electron configurations, so you're going to hear me say it a lot. But just a reminder that out in nature, we're not going around just willy-nilly handing out electrons to atoms, okay? So, in order to make an electron configuration, you first have to know the energy levels of the orbitals. And I have provided you with two handy-dandy graphics to help you understand energy levels of orbitals. Okay? The first one, you have one axis on the side there that's showing you that as we go up on this graph, the energy level for these orbitals is going to increase. Okay, so the 1s orbital down there in blue is the lowest energy level possible for an electron. And then when we go up, 2s has more than 1s because it's in the second shell, right? So it's got more energy and it's further from the nucleus. And then the 2p orbitals have just ever so slightly more energy than the 2s orbitals. They're in the same shell, so it makes sense that their energy levels are similar. However, the 2p orbitals have slightly higher energy levels. And then as we go up, you'll see that the 3s has a whole big jump there between the 2s and the 2p, because we're now in a third energy level. And then that the 3p and the 3d orbitals have just ever so slightly more energy than the ones before them. I do want to point out one anomaly that we'll talk about in more detail later, which is that you'll notice that the 4s orbital has slightly less energy than the 3d orbitals, which means as we talk about filling orbitals, we're going to fill that one before we fill the 3d orbitals. Okay, so when we thought about this early on as a sort of Russian nesting doll situation where you have one level inside another level inside another level inside another level and we fill from the inside out, that's somewhat accurate, but it's not completely accurate because sometimes we're going to fill one shell from it. We're going to fill one orbital from a shell above before we come back and fill ones below. And it has completely to do with the energy level of that orbital. We are always filling lowest energy to highest energy. Okay? There is another diagram on your paper which has a similar diagram showing you the energy levels of these orbitals, right? If you look at the left half of this diagram, it's similar to the first diagram where it shows you the lowest energy level is 1s, and then 2s, and then 2p, 3s, 3p, and then 4s, 3d, right? Same order as before. But you'll notice that on the side here, on the right side, they've given you a nice diagram to show you the order in which things fill. So if you follow the arrows from right to left on a downward diagonal, you'll see that we fill the 1s orbital, and then the 2s orbital, and then the 2p orbital, then the 3s orbital, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on and so forth. So that is the order in which these things fill, which will be important later when we are trying to write out electron configurations. Okay? The order in which these things fill depends on the energy level that they have. Now let's talk about the basic rules for the order in which electrons fill orbitals. Some of these will be very familiar, and some of them will just give you a little more information, okay? So the first one is called the Aufbau principle, which is what we have just talked about, which is that an electron will always occupy the lowest energy orbital that can receive it. That's why hydrogen that only has one single electron, that electron is always in the 1s orbital. It's never in the 3p orbital because the 1s orbital is empty and it's the lowest possible energy level, so that's where the electron goes. This is where it becomes important to remember that little thing we noticed about the 4s orbital being slightly lower in energy than the 3d orbitals, because it's a no-brainer to our brain that the 1s orbital would fill before the 3p orbital, because the 3p orbital is several energy shells above the 1s orbital, so it makes sense to us that it is lower energy. However, we have to remember that just because something is in a higher main energy level does not always mean that it is a higher energy level, and that's the case with the 4s and the 3d orbitals. The 4s orbital is in a higher energy level, however, because of complicated things beyond the scope of what I'm going to explain to you in this class, it is slightly lower in energy than the 3D orbitals. Therefore, it's going to fill first, according to the Aufbau principle. Next up is the Pauli exclusion principle. Okay? This says that no two electrons in the same atom can have the same set of 4 quantum numbers. You are familiar with this, whether you realize it or not, because it's the reason we've been talking about electrons that are in the same orbital having opposite spins. Because they can't have the same 4 quantum numbers. If they're in the same orbital, all of their quantum numbers are the same except for their spin quantum number, which will be different. And that is because of the Pauli exclusion principle. They cannot have the same 4 quantum numbers. Next up is Hund's rule, which has the most new information for you. Hund's rule says that orbitals that are of equal energy and are each occupied by one electron before any orbital is occupied by a second electron, and that all electrons in singly occupied orbitals must have the same spin state. It's a lot of jargon, okay? This means that for p orbitals, and also later on for d and f orbitals, when we're filling those orbitals, each orbital gets its own electron before you go back and fill them with a second electron. Okay? And this is because, as you know, electrons are negatively charged, and if you put 2 negatives by each other, they're going to repel each other. So, unless they have to be in close proximity, the electrons don't want to be in close proximity. It's like if you and your one sibling moved into a room with 2 bedrooms, you would not both share a bedroom and leave one bedroom empty, right? That would be ludicrous. Okay, the same thing is happening here. There's 3 p orbitals. If you have 3 electrons, there's no reason to shove 2 of them into one orbital when there's 3 empty orbitals, right? All of the same energy level. This doesn't apply when the orbitals are of different energy levels, because remember, we're always seeking the lowest energy level, right? But when they're all the same energy level, if they're all empty, might as well put 1 in each before we cram 2 into one orbital. Okay? If you then your parents had another sibling for you, and now you had 3 siblings, well, one of you is going to have to double up, right? That's what happens. If we have like the p orbitals and then we have 4 electrons, then one comes back and joins that first orbital, and then one of them is paired up, and the other 2 just have 1. But as long as there's 3 orbitals, all of the same energy level, and only 3 electrons, then they're just going to fill them singly. And while they are in there by themselves, all 3 of those electrons will have the same spin state. Okay, now that we understand how things fill, let's talk about visual ways to write down an electron configuration. Okay, there are 3 methods, and the first one is called orbital notation. In orbital notation, orbitals are represented with lines or boxes, with the orbital's name written under them or sometimes above them, depending on who drew it. And the electrons are indicated with arrows that are either pointing up or pointing down to represent spin. So there's a lovely example here for you, okay? You can see we have a box that's drawn for the 1s orbital, for the 2s orbital, and then there are 3 boxes drawn because there are 3 2p orbitals, okay? And then the order in which these would fill would be you'd have this one filled, and then you would fill this one. And then each of these would fill by themselves before finally the last one came back to fill this one, which is why you see the arrows drawn the way they are. So sometimes you'll see people, instead of drawing a full box, they'll just draw a line and write 1s under it, and then draw their arrows above it. But both boxes and lines represent the same thing here. So let's talk about how we got here, because it can be hard to conceptualize how to get started on one of these. So the very first thing you should do is look at the periodic table and determine the number of electrons that this atom has. So oxygen, we see, has 8 protons, which means that in a neutral atom, it's going to have the same number of electrons so that it's electrically neutral and they balance each other out. So we know we have 8 electrons that need somewhere to go. So we're going to take a look at that chart from the beginning of your notes and find out, okay, the lowest energy level, the lowest orbital that they can join is the 1s orbital. And we know that we can only fit 2 electrons in each orbital. So we know the 1s orbital is going to fill up with 2 electrons. Then what's the next one that comes? Well, you can go back and look at that chart and see that the 2s orbital fills next. And so we put 2 more electrons in it because the 2s orbital can only hold 2 electrons. So now we're up to a total of 4 electrons, and we still have 4 electrons that need a home because in total we have 8. So then we know that the next orbitals available are the 3 2p orbitals. So they're going to fill next. And thanks to Hund's rule, we know that each of those orbitals is going to get 1 electron. And then we come back and take that last electron and put it back in that first orbital, because after all 3 of them have 1, then one of them can have another one. Okay, so that is how we build this electron configuration. Now, drawing the arrows like this works really well for about the first 2 periods on the periodic table, because they have a very small amount of electrons, right? Neon, which is the last one in the second period, has about 10. I don't know about you, but if I have to draw more than about 10 little arrows, I'm starting to get tired of it, right? So there is another method for writing down an electron configuration, and that is called electron configuration notation. In this one, we do away with any lines or boxes or arrows, and instead, we start with the level designation, 1s, and then give it an exponent to represent the number of electrons that are in that orbital. So, for example, the electron configuration notation for oxygen, we would again start with the 1s orbital, and we know that it's going to be full, so we're going to put a 2, because it can hold 2. Then we're going to say the 2s orbital, and we know that one's going to be full as well, so we're going to put a 2. And then we're going to say in the 2p orbital, we know that this one's not full because in total, the 2p orbital could hold 6, but that would put us at a total of 10 electrons, and we only have 8. So if we have 4 already in orbitals, we only need to put 4 electrons in this last one, so we're going to put an exponent of 4 here. So that just looks like this: 1s2, 2s2, 2p4. Elements that are in the first and second period are going to continue to fill sublevels following the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Okay? And it's because of those rules that we know that no electron is going to be able to occupy a higher energy sublevel until we fill the sublevel below it. When one shell is filled and the one above it begins to fill, then the shell that was filled now becomes inner shell electrons because they're no longer in the outermost energy level and therefore less likely to interact with other atoms. Okay? So hydrogen and helium are both holding all of their electrons in the 1s orbital. So for hydrogen and helium, the 1s orbital is their outer shell. But when we get to lithium and beryllium, they have electrons that are in the 2s orbital, which means that the 1s electrons become inner shell electrons. They're no longer in the outermost energy level. When an atom, like neon, has 8 electrons in its outer shell, it is said to have an octet. Having an octet makes you extremely stable as an atom. You are not likely to interact with other atoms if you have an octet because your outer shell is completely full. So if you look at neon, neon would put 2 of its electrons in the 1s orbital, 2 of its electrons in the 2s orbital, and 6 of its electrons in the 2p orbital. So that outer energy level, the 2 energy level, n equals 2, is full. Right? The s orbital and the p orbital, which are the only orbitals in that shell, are full. So it has 8 in its outer shell, and it is having an octet. So it's very stable. And we call these the noble gases. They are the last atoms in their period, and on my chart that's on the wall, they are pink. Okay? So helium, neon, argon, krypton, xenon, radon, and one that's sort of undiscovered and I don't think named yet, are the noble gases. Helium gets to be a noble gas even though it doesn't have 8 electrons in its outer shell because its outer shell is still full because it's just the 1s orbital, right, which can only hold 2, therefore it's full with 2 instead of 8. Okay. Now, you might be wondering, Mrs. Von Lau, why are you telling us about noble gases right now? Well, understanding noble gases will help you with the last form of notation, which is called noble gas notation. It's the final method we're going to discuss for writing electron configurations, and in this method, we replace the first portion of an electron configuration notation with the most recent noble gas in brackets. The rest of the notation is then written out, the same as the electron configuration notation. This is just a method of doing it shorthand. It makes it easier because as we increase, right, when we get down to like iridium that has 77 electrons, that's a lot of orbitals to be writing out every single one, right? Your hand is going to cramp and get tired. So by replacing the first portion of that notation with the noble gas, we shorten the amount of writing that we have to do. Let's do an example of what this looks like. If we are doing the noble gas notation for silicon, we first need to look on the periodic table and figure out which noble gas is the most recent. It has to come before silicon on the periodic table. So the correct answer here would be neon. Okay? If we were to write out the electron configuration notation for neon, we would write out 1s2, 2s2, 2p6, okay? Because it has that outer shell full. So the N equals 2 shell is full. It's got 8 electrons in it, and then the other 2 that belong to neon are in the first 1s orbital. Okay, so this is equal to neon. So now, instead of writing out 1s2, 2s2, 2p6 for silicone, which it will still have because all of those orbitals have to be full in order for us to get to the higher level ones, instead of writing all of that out, we're going to take a little bracket and put neon in it. So it's like substituting this portion of it in here by saying neon instead. And then we know that silicone has 4 more electrons than neon. Neon has 10, silicone has 14. So we still have 4 electrons that need places. Well, after the 2p6, if we go back on our chart, we can see that the 3s orbital is the next orbital to fill, right? So then we're going to say 3s. The 3s orbital can only hold 2 electrons, so we're going to put them here. And then we know that the next orbital that's going to be filled is the 3p orbital, and we only have 2 electrons left, so we're going to put them in this orbital. So this right here is the noble gas notation for silicone. Notice how we replace the first half of that, and we just write neon instead of having to write out 1s2, 2s2, 2p6. It makes it shorter. Okay? And you can continue to do this as you go down the periodic table. You'll just pick a different noble gas. So for silver, we would use krypton because it's the most recent noble gas. And it cuts down on the amount of writing that we're going to have to do. So there's your noble gas notation. Now, atoms in the 4th and 5th and 6th and 7th periods are going to continue to fill, mostly as you would predict using the Aufbau principle. There are a few exceptions. So, for example, chromium would not be predicted to have the configuration that it does. The configuration that chromium has is 3d5 4s1. So you'll notice that what's happened is not only have we added another electron to the 3d level, but we've borrowed one from the 4s level, which should be full. Because if you remember, the 4s level is slightly lower energy than the 3d level. So it's weird, and it's not how we would predict it. Explaining why things happen this way is beyond the scope of what we're learning in class. The most explanation that you need to understand is that for whatever reason, this new configuration is more stable for chromium than the one that was predicted by the Aufbau principle. And the same is true for several other atoms that are in periods 5, 6, and 7 that deviate from the Aufbau principle by pulling electrons down like this or filling in an order that you might not predict. It's simply because whatever configuration they choose to be in is somehow more stable for them. And the explanations of why that's more stable is beyond the scope of what we're going to discuss in class. It's also important to note that the 5d orbitals and the 4f orbitals are so close together in their energy levels that there's lots of deviations from the Aufbau principle here, because those orbitals are so close in energy level that electrons fill them differently than we might anticipate. Now, if you want to see these configurations and how they deviate from what you might expect, there are tables in your book. They go through the first, second, third, fourth, and fifth periods in the section 4.3. And then the 6th period ones are in an index in the back of your book. And then I believe they did not include the 7th period ones because they're very strange and partially incomplete. Okay? But they're all there available for you to look at in case you're curious about what their configurations actually look like. I'm not going to ask you questions where you have to complete electron configurations for ones that are outside of the Aufbau principle. And if I do ask you questions about ones that deviate, then I will indicate that they deviate and that you need to look up the answer in a chart instead of trying to figure it out on your own. Okay?
So we won't need to know